Hello, and welcome to AMAT502 Lecture 5. In this lecture, we're going to discuss more about recursion, focusing on operations on strings and on lists, a data structure which we've used implicitly at least once before, but we'll explain in more detail now. So I just want to alert everyone to some resources. In addition to the MIT book that we've been using by Tutor, we also have a very good book coming out of some professors at Harvey Mudd called CS for All. This book is used for freshmen at Harvey Mudd and is required by all students to take. I find it to be a really good resource, although maybe it focuses on things for a little longer than we need to in this class. The real bonus is that attached to this book is also a collection of free exercises, which you can see by navigating to this website. PicoBot provides sort of that approach to programming that was pioneered by the concept of using a turtle that you would move around. But we've been mostly focusing on things related to Chapter 2. And just like we have this hierarchy of greenhorns, neophytes, apprentices, and so on, you might find it useful to engage in some of these exercises. So that's just a resource alert. And these are all free, although the textbook itself is not. Okay, so one thing which I observed in some of our breakout sessions was that it wasn't clear enough in what were the key ingredients in recursion. So I'm going to go ahead and highlight that here. So remember, the definition of a recursive function is one that makes reference to itself. Very often, colloquially, people think about definitions that are circular. These are definitions which use the word you're trying to define. And normally, we have this impression that circular definitions are useless or somehow to be avoided. But in recursion, we actually can make use of a reference, make use of a definition of a function that makes reference to itself, as long as we vary the argument input. The way in which we vary this argument input often involves restricting to a subset of the problem, or perhaps a lower number or a substring. Eventually, we want to reduce to something called the base case, and we always need to end in some base case. So it's very useful to try to think about what are the base cases when approaching how to code a problem up using recursion. For example, when we looked at the definition of factorial, something many of you have seen, we start off with the base cases, plural, that both 1 factorial and 0 factorial are equal to 1. Then for all larger n, we can define n factorial as n times n minus 1 factorial. And so, although this is a recursive definition, it reduces it to a definition using things that were defined earlier, such as earlier factorials. So by now you've already done your problem set 1 and have enjoyed using some of these definitions for how to define factorial, both using iteration and using recursion. So the difference between an iterative implementation and a recursive implementation is an iterative implementation isn't recursive, meaning it doesn't make reference to itself. But it often solves the problem by using either a while loop or a for loop that steps through and iterates a certain quantity. So for example, in this factorial loop definition, we start off by defining this total, initializing this variable to be 1. Set j is equal to 1. And then while j is less than or equal to n, where n is the input, we're going to multiply total by total times j. That just records in that expansion of factorial, let's say n times n minus 1 times n minus 2, and so on. Here we are stepping through the total by multiplying by whatever is increasing. And so we then increment our variable. We are in a while loop and we want it to stop. So we need to use an incrementing or decrementing variable. And then we repeat this until this condition's no longer satisfied. So that's the iterative implementation of factorial. The recursive implementation, by contrast, makes reference to itself. So you'll see that there is a situation in where as long as n is not equal to 0 or equal to 1, then we are in the else case, where we return n times factorial, which is the function we're defining. Notice it's the same here and here. This is what we call the recursive call. But again, the other reason this doesn't loop forever or cause one of these recursion depth exceeded errors in Python is we have this base case, which we assume is going to be reached by our argument input. Okay, so I recently discovered this wonderful tool, again, with the help of this book, CS for All, which allows us to visualize how functions are called, how variables are stored in memory, and how they're put together to make computations. If you navigate to this website, Python Tutor, you might expect a larger suite of exercises. But really what this is doing is it's getting to explain to you under the hood, how are functions and variables defined and operated on in Python. The key idea here is that we start with initially a frame, a global frame. This is where we define our functions. And every time we define a function, we're just putting something into memory. We don't necessarily call the function until we've actually are evaluating it on some value. And in that case, we do actually create new frames, and we create a new frame for every function call. Navigating back to our slides for a moment, let's consider the following Python program. Again, Python program is just a sequence of definitions and commands. So in our first line, we just define g of x. And then we perform some operation using x and call that our result. Result is equal to 4 times x plus 2. Then, like all good functions, we have to have a return statement. Otherwise, it's going to return a none type. We also define another function, demo of x. Notice it's the same argument, but it's not going to cause any problems because x is a local variable. Demo of x creates 2 more quantities, again, local variables, y, which is going to be x when we divide by 3, producing the quotient and not the remainder, and then z, which calls g on this newly divided number, the quotient, when we've divided by 3. And then it returns the original argument plus y, or y is going to be x divide by 3, and z, which is going to be the output of this call to g. So these are 2 definitions, which Python just takes into memory. It doesn't actually evaluate them until the functions are called. That's what finally happens in this third unindented line, these being the first 2. So it calls demo of 15. And if we just sit and we look at it, we can read the program and see how it should work. So demo of 15 binds the value 15 to x, divides by 3 to produce y. Luckily, 15 is divisible by 3, it's 5. So now y is 5, and then it calls g with the value 5. So 4 times 5 plus 2 is going to be 22. That's z. So now we finally hit our return statement. It returns x, which is 15, plus y, which is 5. 15 plus 5 is 20. And then it adds the output from g, which is 22. So 15 plus 5 plus 22 gives us 42. Very special number. Let's go ahead and use this Python tutor to visualize some of these, to visualize how this execution actually occurs. So I've created a link which goes directly to this code and shows how it steps through. You'll see that there's a red arrow which shows the line that's about to be executed. And here we are. You see it's the next line to execute. All right, it defines g of x. That creates an object, which is a function in memory. All this is sitting inside of our global frame. It's kind of like the main file if you programmed in C++. All right, next line to execute is the definition of demo. All right, and as I alluded to, it just establishes that there are these objects that exist. It doesn't necessarily evaluate them. And in fact, the third line to be executed here is actually demo of 15. This is finally where something's going to happen. We're calling the function. So let's pay attention to what's happening up here. We've got our frames, and we've noticed that there are places that are stored in the memory for g of x and demo of x. All right, and our next line, that was just in our third step, we called demo 15. What this does is it brings into memory another frame, sometimes called a stack frame, which then binds the value 15 to x, and it returns to the evaluation of demo of x with this value, x equals 15. It then proceeds to actually evaluate all of the lines in the indented body of code. It computes, all right, y is equal to, in our next step, we're going to say y is equal to x divided by 3. We see that in that frame, that creates another local variable, y, whose value is 5. And then in this next line, it creates a local variable z, which is going to be the output of g of y. But in so doing, we've actually have to go back up and remember what is g and how does it work. So we turn now to the definition of g of x. Now x, again, this being a local variable, is actually 5. So even though these look like they're using the same letter to refer to different numbers, there's no contradiction because the scope of understanding for each of these variables is restricted completely to the internal operations of these functions. All right, so as we process our way through g of x, we see that it goes to the line where I now take 4 times my argument and I add 2. That gives us this result, 22, and it now returns 22. In that next step, we've collapsed the frame, which was responsible for evaluating all the inner details of g of x. And we've now produced this new value, z, inside the frame belonging to demo, which is 22. We step back, we see that this was exactly the return value from g. G of y produced 22, which then got bound to z, which is now a local variable that's within the purview of the demo function. Finally, we're about to return the sum of these things, and it returns our value, 42. And that's the end of the program. So if we go through, we can also understand various implementations and the differences between an iterative implementation of factorial and a recursive implementation of factorial. So let's go ahead and look at that. All right, so here we have this iterative implementation of factorial, where again, as I step through the program, it first creates an object called factorial loop. And then it actually skips all of the indentation to go to our next unindented line. That is factorial loop called on the value 4. So it wants to compute 4 factorial using a while loop. So now that we've actually called the function, it goes back and looks and says, how does factorial loop work? Let me start to execute this line by indented line. So we now call the function. We're now looking into the internal mechanics of factorial loop. And this goes through that whole process we just described, where it initializes some variable total, creates some incrementing variable j, and then it steps through this while loop enough times to start computing our total via incrementing and multiplication until we actually finally get to our total equals 24, which is going to be the value of 4 factorial. 5 now exceeds this, now returns 24, and we're at the end of our program. Let's see how this differs when we use the recursive implementation of factorial. So the first thing I want you to note is that there's already 2 fewer steps using recursion rather than iteration. You just remember we had 20 steps when evaluating the iterative implementation of factorial. With recursion, we've already managed to carve off 2 lines. And part of this has to just deal with the way we arranged our variables, but hopefully this illustrates some of the power. Now let's see what Python Tutor does for us here. All right, as we've said, it goes to the first unindented line. That's our definition of factorial. And it just says, I'm going to store this object factorial in memory. And then I go to my next unindented line. It's factorial 4. We now call that function. We need to evaluate this function bound to this input, whereas n is equal to 4. All right, so now we can get into the actual mechanics of this recursive implementation of factorial. So we've started the call. The next line to execute checks the base case. It asks, does 4 satisfy the base case? It does not. So it skips to the else line, which then immediately goes to this next, our first recursive call. So let's pay attention to what happens here as we initiate our first recursive call. Because n is not equal to 4, it's not one of our base cases, we've now been put into this else statement. So when we finally call that else statement, it invokes another call of factorial, but now the value bound to n is 3. So this is why this isn't truly circular. Actually, every function call in Python just creates another frame in memory with a different value bound to it. So there's not really any self-reference happening. Really, we're calling factorial n bound to 3, whereas before we were calling factorial with n bound to 4. And then again, we step through, we check the base case, it's not satisfied. So then we initiate our next recursive call with factorial bound to with n bound to 2. Notice we've now got 3 frames, which corresponds to the fact that we've called the factorial function 3 times so far. All right, go through one more time. Again, we're not in the base case. So we do our 4th and final recursive call of the factorial function. All right, let's make sure that's actually what happens. Okay, we're about to execute the line that belongs to the base case. N does equal 1. So now we just return 1. We don't return a function call to factorial. Now we've actually outputted a value. And notice that practically every call to factorial will eventually end where its return is just 1, because that is what 1 factorial is. It's just 1. That value then populates up to be combined with the return value of 2 times factorial 1, which then pops up another level to bound to 3 times factorial 2, which now gives us 6. And then finally, that whole number, 6, is returned and multiplied by 4, which was what happened during our first recursive call of factorial. We did 4 times factorial 3. 4 times 6 is 24. And that's actually what 4 factorial is. And we've stopped now with 18 steps. All right, so far what we've been looking at may seem kind of boring. We've done some basic recursion applied to the factorial construction, which we all understand. But soon we're going to understand something called the edit distance. We want to understand a recursive implementation of the edit distance. We're going to need to build up some more machinery before we get there. But one thing we really want to make sure we understand is operations on strings. So let's go ahead and get into the implementation details of strings, how they work, and what are some operations we can perform on them. All right, so as we've already alluded to in earlier lectures, you can always take a string and one of its attributes is its length. And we access this just using the value, or len, that's short for length, of our string s. This is actually a function call, which takes in our string and then produces a number, namely the length of that string. Now there are other things we can do, and this is one of the key differences between strings and other scalar data types like integers or floats or booleans. They have substructure, which means in particular that we can access entries in a string according to their index number or their position. So s square brackets I is the notation for returning the ith character in our string, where we need to make sure we understand that we're counting starting with 0. All right, so as a quick pop quiz, why does s, where we call for the position that is in the length, return an error? Well, let's see. Define a string, my Sharona. And let's go ahead and evaluate some of these arguments. So I'm going to print the length of s is whatever the length of s is, and the character at index 1 is s of 1. So notice when I do that second print statement, it returns y. So this is where we need to be careful about what we're saying in English versus what we should say in Python. When I say s of 1, you might think that's the first position, but actually the very first thing is the 0th position or the 0th index. So position 1 actually refers to what's in the second entry. Now let's see what happens when I try to call s of length of s. You get an index error, and it actually tells you very helpfully, string index out of range. That's because even though the string is 10, if I look in the 10th position, and I use Python speak, that means I'm actually looking for what I would encounter in the 11th position, because I normally think there in terms of what's first position, that corresponds to index 0. So what would correspond to index 10 in Python speak would actually be position 11 in English. So the only thing to actually access this last entry is to look at length minus 1. And indeed, I do access A. All right. So let's move on. And I will put this code back for future Justin. All right. So here's some other things we can do with strings. We've already seen that I can pass square brackets with a single integer entry, and that asks for whatever's in the ith index, where we know we start counting at 0. Index 0 is actually the first entry. So if I want to access a whole substring, I can use the notation I colon 2 dots j. And what that does is it produces the substring that lies between index I and index j minus 1. Again, the subtraction by 1 just has to deal with the peculiarities of starting with index 0 as your first position. There are other sort of default values that we can use here, such as si colon, with nothing entered after the colon. What that does is it takes the string, starts at position I or index I, and then returns the rest of the string. Similarly, we could provide just the second entry, and then it'll assume it wants to start at position 0, the thing that's in the very first slot. So this thinking of strings as like an array or something that has slots, it's very useful, and you just need to keep your mind clear about how Python is referring to indexes. All right, so if we step through some of this, again, this is using my Sharona, you'll see that s from 0 to 6 does produce a string of length 6, where I keep that space as the third character, and then I have SHA. And indeed, that corresponds to whatever is the entry here, even though I know that it's actually going up to what's called index 5. So let's go ahead and understand what some of these other operations produce. All right, so this starts at position 1, which is actually, or index 1, which is the second position. This takes 6 onwards, versus what you can ask is actually in the 6th position, which is R, or index 6. And then you'll notice that this also gives the same output as that. So I encourage you to play with some of these things and see what different outputs you get. All right, so let's try to connect something we tried to do in one of our live exercises, but connecting the ideas of recursion and operations on strings. So here's one way that you could have solved one of our in-class exercises, how to reverse a string. So here's a function, reverse, where I first check my base case, which is going to be what happens if I have the empty string. The empty string, there's nothing to reverse, so you should just return the empty string. The way I can check whether or not I have the empty string is by computing its length and then asking if that is equal to 0. Again, Python needs equals equals in order to test equality, whereas a single equal sign is for variable assignment. All right, if we're not in the base case, what else do we do? Well, we can get to the actual recursive mechanics of reversing this string. Really, if you think about reversing a string, all you're doing is taking the first entry and you're making it last. And indeed, that leads itself to a really nice recursive recipe. If I have a string, I take the first entry and I make it last. I can then recursively call that procedure on the remaining string, take its first entry, make it last, and then recurse further, and then keep doing this. And eventually you'll wind out where the last element of our string is the first returned value, which then populates up using this concatenation operation. That's plus. Plus stands for concatenation when applied to strings. And moves all the way up through. So if we go ahead and use our Python tutor, we can really understand what's happening here. All right. So I've already defined the function for you. We now know how this should work. It executes that line and then goes to the next non-indented line. This is a print command, which knows it needs to evaluate the reverse function on spam. So it goes ahead and creates a frame dedicated to evaluating reverse on the string spam. And again, it checks, is the length 0? It's not. So it moves to our else statement. And now it does our first recursive call, where we now call reverse on what was between index 1, that's the thing in our second position, onwards, which for spam means Pam. Then go through, now we're evaluating reverse on Pam. Check the base case, it's not satisfied because the length's not 0. And now we initiate our second recursive call. Okay, so we have now pulled off the first entry of Pam, that's P, and now we're recursing on AM. Again, length's not 0. And so we do now our third recursive call on the one string M. All right, so it's gonna go through. Base case is still not satisfied, although it's arguable whether or not it's necessary to have this line. And you might think about, how would I modify that if statement to have fewer recursive calls? All right, so we go through and we do our fourth and final recursive call. We're recursing on the empty string. We move through, finally we satisfy the base case. We return the empty string. That's the value that's being returned. We then return the value M. And now MA, because what's it doing? It's returning now the reverse string of AM, which is MA, which then produces the reverse string of map, of Pam, which is map. And then we get finally the return of the reverse of spam, which is maps. And that's it. 22 steps to reverse spam. All right, so here's some more things we should know about strings. And this is the first time we're going to use really radically different notation in Python. Normally, when we have a function has arguments that are enclosed in round brackets. Here, we're going to start introducing a suite of operations where the way we execute them is by taking an object, like a string, and then having a little dot, and then some operation we want to perform on that string. And here are some examples of these operations. So we could do lower with empty round brackets, and that will make all the characters lowercase. We could also do upper, which will make all the characters uppercase. And we could also do replace, where I actually provided an argument, and it just replaces every instance of the thing that's in the first slot with the thing that's in the second slot. So if I wanted to go ahead and make all the letters in my Sharona uppercase, I could execute this code. So let's go ahead and just see that real quick. All right, so here's S equals my Sharona. I take S dot upper. And that's gonna evaluate to my Sharona. Now all uppercase. Now, if I just go ahead and look at what does S look like, even though I've applied this upper operation, it returns the original string. And again, remember, when we're just doing a code cell, we're not using print statements, it's just gonna evaluate the last thing that can actually be evaluated. In this case, S is gonna return the value for S, which is our original string. So I'll just make a disclaimer that there are lots and lots and lots of operations on strings. And I encourage you to read the Forgotten Manual. This is documentation on aspects of string in Python, according to Python 3.8. And there are lots of things you can do here. Additionally, here's a perhaps more user-friendly, or at least visually friendly, set of methods that you can apply to strings. And you can see there are dozens, if not hundreds. All right. So far what we've been looking at is recursion, aspects of strings, and we've noticed that strings have internal structure, which we can slice and produce substrings that exist between various positions. All that is actually reminiscent of a new data structure, which we've sort of danced around, called lists. Lists are defined just using square brackets. And all of the methods that we've used on strings can actually be used on lists, although they'll have slightly different behavior. Let's go through some examples. All right, so here's a string, sorry, excuse me. Here's a variable A that we're binding to the list. I know that because there are square brackets where the entries are cars, separated by a comma, boats, separated by a comma, 2.718, 2818, another comma, 3. And so here's what happens when I evoke each of these methods, or each of these operations. So if I print A between index 1 and 4, what do you think is going to happen? Well, remember, index 1 actually corresponds to the second position. So it should produce boats all the way up through the end here. Now, what is going to happen with each of these other entries? Well, let's go ahead and just evaluate this. All right. So what I said would happen with the first print statement was true. It started with boats, and although it changed the number of quotation marks, all it's saying is, like, I recognize that in position 1, or index 1, there is the string boats. And then these other places, there are these numbers. All right, so what do I do in each of these other operations? If I take the first entry, again, using Python notation, that's going to correspond to boats, and I add and ships, that's going to concatenate and ships and store that in my list, at least the position at indexed at 1. And indeed, if I print A1, it's going to return just the string boats and ships. But if I ask to print all of A, it's going to give me my whole list with the new updated entry. A of 3, which again actually corresponds to our last entry, 3, that exists in index 3, position 4, and it updates it by adding 3. And you can see that here, both when we evaluate it and print it, and when we return the whole list. Finally, in this last setting, we do an operation where we go ahead and view the third entry as a string, and then we add 3 viewed as a string. What happens in this case is it concatenates those 2 characters viewed as strings to produce 63. Here are 2 more operations you can perform on lists. And one thing to note is that lists, in contrast to strings, are called mutable objects. That means we can perform these methods and they will actually fundamentally alter the attributes of these objects. So here are 2 examples of that. Given a list, I can always append another list or append an item to the end of that list. And I could also insert an item at a given index. So for example, if I have a list which consists of statistics, algebra, topology, and statistics, that's a list with 4 entries, one of which is repeated. I want to append the string analysis, then it does exactly that. I can also insert at index 1 the string complex analysis, which puts it in second position right there. You'll notice that there are going to be, that you can repeat entries, and that's completely fine with lists, but other data structures, not so. All right, finally, another 2 I want to introduce. We've just talked about how to reverse a string using recursion. You might ask, how do we do that with a list? Well, you could certainly create your own reversed implementation. But that's also an attribute, or a method, I should say, that we can apply to a list. So one of those is reverse, and another one here is sort. And the way you would call both of these methods is by taking my object, having that dot, and then whatever the name of that method is. There is actually a function analog of sort, and that's called sorted. But we're about to see how that differs. And if you want to read some more, I refer you to this article. Well, let's go ahead and see this in action. All right, so suppose I've got this list 0 with statistics, complex analysis, algebra, topology, statistics, and analysis. Okay, there's a mouthful in there. Now, how can I apply these sort operations? Well, luckily we can always compare and order strings based on alphabetical position. A's come before B's, B's come before C's, so on and so forth. So let's suppose I take my list 0, and now I create 2 more lists. List 1 is going to be sorted of list 0, and list 2 is going to be list 0 dot sort. So if I print list 1, this is the one where I've applied the sorted function, you'll see that it accurately resorts my list so that it's increasing in dictionary order: algebra, analysis, complex analysis, statistics, and topology. Now I can also try to print list 2. Let's see what happens. It says none. It's a little odd. Let's try to understand why that's happening. Well, indeed, if I check the type of list 2, it's going to return none type. That's because with these methods, you don't want to necessarily think of them as functions where they actually return values. Instead, they're modifying attributes. And so we're stuck in this situation where what we have here is list 2 equals list 0. We're not allowed to do that all in one line. But let's see what would happen if I were to delete this and, of course, delete that line because I don't have any knowledge of it. Now let me call list 0. So notice that when I've called this dot sort, it's now changed the attributes of list 0 to be in dictionary order. And if I write list 2 equals list 0, I won't have any trouble. And indeed, I ask what's the type of list 2, it now understands that this is a list. So this is just one of those examples where you can't do everything in a single line. All right, so now at the peak exercise for today's lecture. So I want to understand lists and recursion. In the next lecture, we're going to consider the edit distance. But let's start to gear up our sort of recursive and algorithmic thinking. Let's consider the subset sum problem. So you would imagine here that someone's given you a list of items for delivery, but you also know that you only have a capacity to carry so many items, where capacity is, say, determined by size of the elements in this list. So for example, someone says, I've got a thing that takes up 5 units of space, 10 units of space, 18 units of space, 23 units of space, 30 or 45. But I know that I can only carry 42 units of objects on my delivery truck. How might I go about selecting items? And again, I want to try to think algorithmically. So here's the first approach that you might take. I'm going to take my list, and I know what my capacity is. And I'm just going to scan from left to right, and I'm just going to agree to ship everything in the order that I see it until I've run out of space. So sort of like if you're packing up a moving truck, you just sort of haphazardly start putting things in without deciding how and what order you should put them in. So how would that work? Well, I start by stepping through, looking at this thing that's in index 0, that's our first position. See that it only takes 5 units. That's certainly less than 42. And so I add it to my list of things to ship. I then go on and I say, all right, let me take the next item. That's going to be given by my list 1. And we know that the size of that thing is 10 units. And I've already agreed to ship something that has 5 units of size. So I'm now shipping 15 size units, still less than my capacity of 42. So now I go on and I go to the third entry. That's my list 2. And if I sum up its size and all the previous sizes, I get 18 plus 15 equals 33. Still less than 42. So we're in the clear. So now I go to look at the 4th item on my list. That's the thing that exists in index 3, my list 3. And I try to sum up its size along with the things I've already agreed to ship. And I'm now way over budget. I can't ship that item. And so in this sort of naive attack on the subset problem, I have to halt and agree to only ship the first 3 items, and I've used 33 units of my total 42 units space. So here's some questions that I want you to consider. Can we do better than 33? And what choice of list entries achieves this maximum result? So let's go ahead and look back at our list and think about it. Well, if I had sort of this God's eye perspective on the problem, I could say, oh, I could certainly do better than 33. Just off chance, if I looked at something that was size 10 and something that was size 30, I'd use 40 units of my space, which is pretty near optimal. But what is the optimal entry? Well, it actually turns out that shipping these middle 2 items, 18 and 23, that uses up 41 of my total 42 units of space. And so the question is, how do I go about parsing items, which items to ship, to maximize the use of my space on my delivery truck? And then also, let's think about what would happen if I were to apply this method I just did, but when the list wasn't necessarily ordered, or even it was just given to us ordered, but ordered backwards. That'd be a situation where I would immediately stop and not be able to ship anything beyond that. Or perhaps I would first check, is this thing larger than what I can handle? Well, yes, let's not include it. And then go to the next item. That has 30 units. And so you'd agree to ship that. But then when you try to ship the next item, 23, you would stop. So various ways of approaching this problem with this type of attack is going to result into all these suboptimal solutions. So let's go ahead and maybe try to clarify our thinking by coding that up and seeing if we can do better. All right, so I already made an allusion to how we might actually implement that strategy. But let's go ahead and see how to do it using recursion. And one of the things we'll consider is maybe other ways of implementing that strategy. So let's give a recursive variation on this. Go through the list in order and then add things until I exceed my capacity. But let's also be a little smarter and check whether or not the thing I'm adding is already larger than my capacity. All right, so let's call this function SubsetSum1. I have a capacity and a list. And I've written a docstring to specify how I should use this function. So the first thing I'm going to say is if my capacity is already less than or equal to 0, I'm not even going to attempt to do anything. Just say that I'm shipping 0 things. Alternatively, if my list is empty, there's nothing to ship, then I should also return 0. These are the base cases. All right, so now let's go through and think about this. Add the first thing on the list. Well, one way of doing that is by creating this new variable first and setting it equal to the value of what sits in the 0th index, which is the first position, my list 0. And then I'm going to separate off the rest. That's everything that lives between first entry according to Python onwards. Now I'm going to go through some various checks. So the first thing I'm going to check is that first entry already larger than my capacity? No. If it is, this is where I'm going to do something a little clever. I'm just going to disregard it and try to apply my function, but now using the rest of the list. This was like in that situation when I was calling it on the backward string where it starts with 45. I go ahead and reject 45 and then move on. Alternatively, if the first item in my list is equal to my capacity, then I know just by shipping that item alone, I've maximized my utility and hit my capacity. Finally, the interesting step is, let's assume that the first entry in my list is less than my capacity. And then I'm going to return, I'm assuming I'm shipping that first item. So that is going to be the size of what exists in that first position. And then I'm going to add to it the capacity of the things that I can ship using the rest of the list, accounting for the fact that I now have reduced capacity. I've reduced my capacity exactly by the amount of first. So let's go ahead and store this function definition in memory and see what happens. All right, so here is our test list, 5, 10, 18, 23, 30, 45. Let's go ahead and call it. All right, so it achieves exactly the output we just described, which is I ship the first 3 items and use up a total of 33 units of my capacity. And let's try to answer that other question. Now we'll use our reverse method. So test.reverse. Notice it doesn't output anything because it's not returning a value. It's just modifying some internal details of that list. Test. Let's check that that actually is what happened. Yes, when I call test now, it knows that its attributes have been modified, and in fact, it's now been reversed from what it was originally. So now test is 45, 30, 23, 18, 10, 5. And now let's call subset1 now on test, which is different than the test up here. So we notice that using this algorithm, we've already been able to do better. We were able to ship 40 units of stuff. Let's understand how we actually got that 40 number. And we can also check, if we're very skeptical, that indeed that's the output applied to that list. All right, great. So let's focus on the second call, and we'll use again our Python visualizer. So you'll notice that there are a lot of steps. There are already 52 steps in this program. And let's go ahead and quickly step through what's happening. All right, so again, goes directly to our first actual function call. All right, so now we get to really enjoy the visualization aspect of Python Tutor. So we're calling our function for the first time. Our capacity is 42, and our list has a pointer in memory to this actual list data structure. whose entries are 45, 30, 23, 18, 10, and 5. And they even give the index number according to Python. That's the 0th position, first, all the way up to the 5th. All right, so it goes through and it checks our first case. That's one of our base cases. Is my capacity less than 0 or is my list empty? No. So now goes to the next line that can be evaluated. And this is where it takes first, creates a local variable. You can see that here, and binds it to the first entry of our list. That's 45. Then it creates a second local variable, rest, and assigns to it the rest of the list. Then asks, again, is first greater than our capacity? In this case, it is. First is 45. And so it's going to go ahead and return SubsetSum1, that's the name of our function, applied to just the rest of the list, which creates a new frame where now I've adjusted my list, but I haven't changed my capacity. All right, going through, checks the base case, creates new local variables, internal specifically to that second call of SubsetSum, where first is my first entry of the list, and then I've got the rest, which is now the rest of my list. And it now asks, is first greater than my capacity? In this case, it's not. 30 is not greater than 42. It's also not equal. So now we're into this third if statement. And now we're about to initiate our first really substantive recursive call. We take the value of first, which in our case is 30, and then it initiates another recursive call to SubsetSum, but where I reduce the capacity, I'm assuming I'm shipping that thing that has 30 units to it, and I use the rest of my list, which consists of 23, 18, 10, and 5. All right, so now we go over, create another function frame with now our capacity being the difference, 42 minus 30, it's 12. And where my list is now this much shorter list. And it steps through and it is going to continue to be defeated by this is first greater than my capacity. Because in this case it is. 23 is larger than my capacity, 12. All right, so then it calls it on the rest of the list. And then again, now we create first, that's 18, that's less, or it's greater than my capacity, which means I'm going to be tripped up by my first if statement. Again, I call again. Now with my capacity unchanged, 12, and now it looks to compare with my entry 10. So this is where something interesting happens, because now it's extracted the first value of this list, which is 10, now uses the rest of the list and does our comparison. Is first greater than capacity? No, 10 is less than 12. So we skip these steps and we go to this next one, which is where first is less than capacity. That's 10. 10 is less than 12. So now I return 10, and then I call again on the rest of my list, which only has one more entry. 5 commences our final recursive call. All right, next penultimate recursive call until we produce an empty list. And that's when we're going to encounter our base case. So now we unwind. And you can see that we're about to initiate this non-recursive call because we're now in our base case. We return 0. That binds 0 to this final call of SubsetSum, which then combines with the other value of SubsetSum, which then combines with the one where we added 10. So we turn 10, which then combines deeper with our call from these two other do nothing calls. And then finally, we remember what value was extracted, which was 30 and 10, and we have their sum, which is 40. And then we continue to unwind, and we finally reach the end of the program. I'll leave it to you to go through the initial original call to try to understand what's happening there. All right, So I won't keep you in suspense any longer. And I'll go ahead and present the full solution of SubsetSum. And I'm going to give this its proper name, SubsetSum, where it takes in a capacity, a list, and it looks almost identical. We have check if the capacity is less than or 0, see if our list is empty. We again do the same thing where we extract the first and the rest. We do exactly the same two if comparisons, but we fundamentally change by, instead of assuming that we use that first entry, we're going to also explore the pathway where instead of using that entry, we go ahead and skip it and just go ahead and try to solve my problem on the rest of the list without changing my capacity, because I have not agreed to ship first. And so this call is going to produce 2 forking paths. And at each step, when it goes to compare the return values, it's going to return the max of these 2. Because we're interested in what's the situation where our max is, what's the maximum amount of stuff we can ship. So here it is in a code cell. And if we go ahead and check, how does it work? Notice that we get exactly that optimal solution we figured out by inspection, which was to ship the items that were size 18 and 23. We also notice that even if I feed it the list in a different order, it returns the same value. So there's good reason to believe that perhaps this implementation doesn't depend so much on SubsetSum, although it might actually return different items as long as the total shipping capacity is the same. So I'm going to leave it to you to practice copying that code into Python Tutor and going through the steps. And one of the things we'll be asking during our breakout sessions is, how many steps does it take to execute with the correct implementation of SubsetSum? And then we'll also play a little game, see how we can maybe optimize the efficiency of that code in terms of number of steps by using if, elif, and else statements. And then finally, I want you to think about, or at least make some conjecture on, what do you think the complexity of this SubsetSum function is? Meaning, how many steps, what is a order of growth for the number of steps of SubsetSum as a function of the list length? All right, that's all for now, and I look forward to seeing you in class.